Hey there, welcome back to Real Analysis. In this section, we're going to start our work in Chapter 2, talking in the section 2.2 about sequences of real numbers. Um, I'm not going to include it in the video lecture, although you should certainly read carefully Section 2.1. It doesn't really have any mathematical results in it in terms of its content, but it does certainly motivate the chapter. It's a short section, and so you should definitely read over it because it kind of sets the stage for why we want to kind of ask some of the questions that we're going to ask as we proceed through this material in chapter 2. Okay. I'm certainly assuming that the notion of sequence is not new to you. You've all taken calculus courses. Typically, it's in a second semester of a three-semester calculus course where you kind of carefully study this notion of a sequence and limits of sequences. So I'll definitely not, assume that you've never talked about this before, but I'll try to just establish the notation and the formalism that we're going to use to give kind of rigorous proofs of, most of the things I'm going to say about sequences you will have seen in your calculus course. Just our business here is to sort of rigorously justify that business. So we have to kind of give ourselves some firm mathematical foundations to do that. Um, this material is super important. I would highly encourage you, like you do with all sections, but in particular, as we start through chapter 2, you really want to carefully study this, get used to the notation, the terminology, also the proof techniques, kind of how we establish these ideas, because it is absolutely fundamental. It's absolutely foundational for everything we're going to do in our course, and in particular for everything that people kind of think about in this vast subject of analysis. All right, so let's start with the main definition. It is remarkably short. I'm going to kind of reveal all of this here at once. So it's definition 2.1 in our text. We'll just refer to it as the definition of a sequence. So I can kind of underline here for emphasis what term we're defining. As we're defining the term sequence of real numbers. Okay, and very briefly, a sequence of real numbers is just a function. It's a function f, so f is the sequence, but this function's domain is the set of counting numbers, natural numbers, and its codomain is the real numbers. That's why we have a sequence of real numbers. Later on in this course, we'll consider sequences of other objects, sequences of, well, you can think of sequences of rational numbers, complex numbers, but we'll also perhaps look at sequences of functions and some other things. But here, when I say sequence, if I don't mention otherwise, I always mean a sequence of real numbers. And in particular, I mean I have a function that takes a natural number and produces a real number. All right. So, but because the natural numbers are sort of a special set in the sense that we can list its elements, right? We can list out the elements of the natural numbers. They're discretely spaced along the real line. So we have the natural number 1, 2, 3, and so on. So we can also list the outputs of this function. It's not true, say, for a function of a real variable, right? You cannot list the real numbers because they're sort of a larger order of infinity. We'll kind of speak about that a little bit more precisely in this course as well. But because we can list the input values, we can also list the output values. So given a sequence, that is given a function from the natural numbers to the real numbers, I can list its outputs. I can look at f of the first natural number, f of the second natural number, and so on. All right. And just like in calculus, we'll use that same terminology. We'll call these things the terms of the sequence. Okay, so in particular here, if I sort of highlight one by drawing a little arrow to it, I'll refer to this thing as the nth term. Okay, so the first term of the sequence is the value at 1, the second term is the value at 2, and so on. So the nth term of a sequence is simply the function's value at the nth natural number. So exploiting the order of the natural numbers. If I reveal a little more on my slide here, I've got some kind of comments about notation. So although formally, when we work with them, we certainly want to remember that sequences are functions. So any properties of functions, anything that we know about functions can be applied to these in particular. But for notation wise, we kind of won't use this traditional function notation, rather modify it. And you're used to this. We'll write sort of the input value as a subscript. So I'll pronounce that out loud, sub n, f sub n. So f sub n is the nth term of the sequence. Okay, so it's kind of a competing notation scheme for it. The nth term of a sequence, just of a sequence is defined by a function called f, will be denoted by f sub n. The entire sequence itself, remember we said the sequence is the function, typically we denote it by just writing an expression for the nth term inside of these set braces. So it's a little bit of a notational abuse here because a sequence is not a set, it's a function. But typically we think of the sequence, kind of blur the distinction between it and its terms. Its terms are this ordered list, which we can always think of as a set of the outputs. And so that's kind of at least my justification for why we use that notation. It's common, it's the same notation in your calculus book. Last comment about notation, I defined a sequence from the book. They use the letter F because I want you to emphasize that it's a function. So it's kind of phonetic for function, but we won't so often actually use the letter F to denote sequences. Yeah, sequences are often denoted by, this isn't sort of a mathematical rule, of course, it's just kind of a convention that's happened over time, but we tend to use a lowercase Roman letters either at the tail end of the alphabet, like X, Y, and Z, or also at the beginning of the alphabet, A and B. All right. Occasionally, the author likes to use S, sort of phonetic for sequence as well. Of course, it doesn't matter what letter you use to denote the function, but just as sort of a notational comment there. Let's look at some examples. My first class of examples that I have here are so-called sequences that are defined explicitly. So what do I mean by explicitly? I mean, I give an explicit expression for the nth term of the sequence. So here I am using this notation. If we look at our first example here, I write the sequence just with some set braces around the expression that's just the identity function n. So f of n is equal to n. Here I'm actually calling the sequence x. So this is a notational way of just saying, okay, well, I've got something. If you want to be super formal about this, I've got a function called x. Its domain is the natural numbers, its codomain is the real numbers, and its value at any natural number is that natural number. So this is just the identity sequence. So we'll briefly just write all of that down in this form over here. Either just write x sub n is equal to n. I like to be careful and specify what n's I'm talking about. It's the entire set of natural numbers. Or I just write that very briefly like this. Sometimes in your calculus books, you might have seen people decorate this. You can feel free to do it, write n equals 1 to infinity out here. However, I often won't write that. I'm just going to leave it understood that sequences always have that domain. All right. Just really quickly, I won't make this video too long talking about the details here, but my second example, if you fix any real number c, so it's a constant, so from using it phonetically, then this second example is just a constant sequence. Every term is the same number. Okay, so it's an important class of examples, and that's what it would look like in our notation. So if I were to name that sequence, say something else, maybe I'll call it the letter y. I'm just saying that the value of the function at any n is just always the same number, always the number c. All right. Third example, the terms are minus 1 to the n. Maybe I'll call that sequence z. So I'm saying if you want to know what the nth term of the sequence is, you raise the number -1 to the power of n. Of course, that output is either going to be a 1 or -1, depending on whether or not n is even or odd. All right, so that's a third example of a sequence given explicitly. I'll probably move on here. The last example here, I've used X, Y, and Z. Maybe I'll exercise the author sometimes to note these sequences by S. So in this example, it's a rational number. It's the only nth term of this last sequence example 4 is given by n over n plus 1. N is any rational number, or sorry, any natural number. All right, so just to highlight it one more time, these are all examples of a sequence given explicitly. So I'm just basically giving you a formula for the output of this function at the nth input. Yeah, a formula for the nth term. Nice. Sequences can also be defined so-called implicitly. So what do I mean by that? If I define a sequence implicitly, or people sometimes also say recursively, or given a recursive formula, it's a little bit different of a recipe. When you give something implicitly, you specify the first value of the sequence. So here in my example, I'm defining a sequence called x, and its first term is 1. And then you specify the nth term of the sequence in terms of the nth minus first, or more generally in terms of any of the previous terms. All right. So here, this second formula is valid only for n equal to 2. So if I wanted to kind of write out some of the terms here, I could start doing it, right? Because if I wanted to know what is the second term of this sequence, well, this recursive formula, the recursive relation, the thing I'm underlining in red here, it tells me that the second term is 2 times the first term. The first term is specified to be 1, so the second term is 2. All right, and so on. If I want to know the third term of this sequence, well, it's 2 times the second term. That's 2 times 2, that's 4. So unlike the explicit case, where if a sequence is given explicitly and you want to know, say, the 19th term of it, you just let the input value be 19 in your formula and calculate it. If a sequence is given recursively and you want to know the 19th term, like I'm just going to point at my example here, if I want to know the 19th term of the sequence, well, then I need to know the 18th. But to know the 18th term, I would need the 17th. And to know the 17th, I need the 16th, and so on. So you can kind of generate these things one at a time. I've got a second example here, just to kind of illustrate some variety. Here in my second example, the first term of the sequence is the number 0. And then starting with the second term, you compute the value of the nth term by adding 2 to the term that's right before it. All right, so again, that's my recursive relation, or my recursive formula. All right, so both examples 5 and 6 are examples of recursive sequences. The fifth example, yn, is an example of a kind of special kind of sequence called an arithmetic sequence. So let me give you a definition of what I mean by an arithmetic sequence. Here I took this from our text, so that it's a little bit easier to read, and I didn't have to write it out loud, being a little bit lazy. So an arithmetic sequence are also called an arithmetic progression. They mean the same thing. Maybe I could try to write that above here. So I called it an arithmetic sequence. Arithmetic progression, the same thing. It's kind of a simple in the sense it's easy to describe, of sequence, where each term is obtained by from the preceding term by adding a fixed amount. Okay, so that fixed amount is called the common difference. So the author here is denoting it by the letter D. And you can kind of see in the sequence, you start off with something. I usually call that first term the seed, but you don't have to call it that. And then to generate the next term, you add that common difference, and then you add the common difference again, and so on. So these numbers are equally spaced along the number line, along our real axis, our real numbers. The space between any two consecutive ones is D, this common difference. All right. So if you want to write that down in terms of a recursive formula, you would write, okay, well, the first term of the sequence is C, the seed. And then I'm just writing from the formula. This recursive formula is not something I have to prove. The definition of recursive formula says that the nth term of your sequence is the nth minus first term of the sequence plus that D. And that's valid for n equal greater than or equal to 2. So I'm going to make a claim here that an explicit formula for such a sequence, an arithmetic progression, is given by the expression written there. Yn is just C plus the factor n minus 1 times this common difference. All right, and I'm going to prove that. I'm going to prove that claim. So the way I want you to think about this is I've been given this recursive formula. So think of what I'm drawing this red box around as a given. And then I'm making this claim that explicitly the nth term of that sequence is given by that formula. And I'm going to prove that, and I'm going to prove it by induction for n, because really, what am I saying? It's a perfect induction statement, right? I'm saying that for every n, the nth term of this sequence is given by some expression. Well, such a statement is often proved by mathematical induction. Mathematical induction is a nice tool to prove things are true for every n. All right. So I've tried to write out a proof, kind of illustrating some good habits to write an induction proof. So at the beginning of my proof, I'm just kind of indicating that I'm going to proceed by induction. That's what I've written parenthetically here. So I like that form of the induction theorem that we talked about earlier. So I'm going to start by defining a set S. And the set S is just the set of natural numbers for which the equation I claim is always true holds. Okay, so then what am I going to try to do? I'm going to try to show you that that set S satisfies the two properties, the base step and the inductive step in the induction theorem. And if I can, then it's going to tell me that every number is in S, and every number it's being in S is just exactly equivalent to saying that this statement holds for all n. Okay, so now it's just basically a computation. You might have to remind yourself, rewind the video if you didn't jot down this recursive formula that's in the red box, because I'm going to scroll and hide it as we go here. To start off with the quote unquote base step, I'm just going to say, well, y1 by definition is C. It's given in the recursive formula. And C is certainly equal to C plus 0 times D, 0 being 1 minus 1. So if you look at the definition of S, that precisely says that the number 1 is in S. If you want me to highlight exactly where the 1 is playing the role there, it's right there. Okay, so there's our base step. So to proceed by induction, what do? We assume that we have some natural number, n, that does belong to this S, and we want to show that the next natural number, n plus 1, does. So using the red box formula that's no longer visible on the screen, that the recursive formula says that the next term, yn plus 1, is yn plus d. But now I'm going to use my induction hypothesis, right? The number n is in S. So if the number n is in S, then I can replace the expression yn with C plus n minus 1 times d. So what I just highlighted in green there is exactly where I'm using the fact that n belongs to S, okay? But by the recursive definition, yn plus 1 is yn plus d. So I've just got that, yn expression plus d, and then I just do a little bit of algebra. Factor out a d out of this thing. I have a factor out a d out of these two terms. You certainly get n minus 1 plus 1. That simplifies to C plus ND. And just to emphasize it, I'm just trying to write the form again here. So I've written that yn plus 1 is C plus n plus 1, take away 1, times D. And that's precisely what it means for n plus 1 to belong to S. So by the principle of mathematical induction, that formula holds for all n. Nice. All right. Pause the video if I'm talking too fast. You can take a break. I'm just going to keep going so it stays short. Analogous to an arithmetic progression is a so-called geometric progression. There, instead of generating subsequent terms by adding some number that's staying fixed, we do it by multiplying. Right? So geometric progressions, we multiply by some fixed amount. It's called the common ratio, because the ratio of any two consecutive terms never changes. Not the difference, but the ratio. So we call such a thing a geometric progression. Okay? So again, geometric progressions, by definition, that description there, you can pause the video and kind of read it at your own pace. It says that, well, you start the sequence somewhere. It's also got a seed. And then the recursive formula that would come from the definition is that the subsequent term is just this common ratio times the previous term. I'm going to leave it as an informal, I think. I don't think it's actually going to show up in your Turnitin homework, but I hope you'll stop the video and maybe do it right now. It's fresh in your mind. You can prove using this recursive formula. It's going to get its own shiny red box right now. You can prove that the explicit version of that geometric sequence is just C times R to the n minus 1, and that's valid for any n greater than or equal to 1. So I'll leave that as an exercise. Use induction. Why not? It's a nice practice for you. Okay, getting close to the end here. Next lecture, we're going to start talking about limits of sequences, a very fundamental notion here, but this is just terminology and some examples. I want to point out that, where your author points out, that both arithmetic and geometric progressions are more generally, or they're examples of a more general idea, rather, called iteration. All right. So what is iteration? Your author here, by the way, in section 2.1, when you read it, they motivate some of this sequence stuff using something that you definitely bumped into in calculus, an equation solving method called the Newton's method. Newton's method is another iteration process. Iteration is a very natural way to generate sequences. You sort of keep making some new term from the previous term, or again, more generally, more than the previous terms. You're probably familiar with something called the Fibonacci sequence, which is also an iterative or recursive, or it's a recursive sequence where terms are based on more than one previous term. So anyway, I'm babbling here. So what do I mean by iteration? I take some function f from the real numbers to the real numbers. Maybe I should note here that this f is not a sequence. Maybe you can stop the video and kind of say why before I do. I'm not going to give you much time, so hit pause now. But this f is not a sequence because its domain is not the set of natural numbers. It's the set of all real numbers. So you take some function f, not a sequence, but a function from R to R, and then you pick some value c. It's also called the seed. And then you generate your sequence. If you want to write, I've written it recursively down below, but you generate your sequence by starting with the seed, and then you plug the seed into your function f. That gives you some real number. It's in the domain. So you take that real number and plug it into f. That gives you some real number. So you take that real number and you plug it into f. That gives you some real number, and so on. So in terms of a recursive formula, which I have now developed the habit of drawing red boxes around, so I'm going to keep my habit. There's the recursive formula for this thing. The recursive formula generally for an iterative sequence defined by the function f. X1 is the seed value, and the nth term of the sequence is just the function value at the nth minus first term, that recursive formula being valid for n greater than or equal to 2. All right, so this will serve to generate lots of examples for us. Okay, so that's the end of our kind of introduction to sequences and our notation for them. I hope the examples were interesting, and thanks for listening.